Hi, I'm Dr. Andrew Bernard from Michigan Tech University. I'm here today at PCB Piezotronics to give you a demonstration on the concept of transmission loss. We'll start with a little bit of theory. So the transmission coefficient for material is defined as the amount of sound power transmitted through that material divided by the amount of sound power incident on the material. And here you can see an example of that. Here's the incident sound wave. There's a reflected sound wave, which for transmission loss we ignore. And then there's some amount of sound energy transmitted through that material. The transmission loss we typically specify in decibels. So we take 10 times the base 10 logarithm of 1 over the transmission coefficient. So for example, if your transmission coefficient is 50% or 0.5, your transmission loss would be 3 dB. The mass law is a good starting point to estimate relative transmission loss between many panel types. This simplification of transmission loss theory assumes an even distribution of incident sound energy on a panel over an angular range of minus 78 degrees to plus 78 degrees. This is known as field incidence. It also assumes that the panel is being excited in its mass control region, frequency region, shown by the red box here. So our mass law is shown on the top of this slide, and after we simplify for standard atmospheric conditions, it becomes very simple. All you need to know is the surface mass density and the frequency of the incident sound. For this demonstration, we'll actually be demonstrating insertion loss, which is a slightly different measurement than transmission loss. Transmission loss, remember, is a ratio of power. Insertion loss is a ratio of pressure with and without a barrier, and is much easier to demonstrate. The fundamental loss mechanism in the material is the same, it's just a different measurement technique. So we'll be showing the demonstration of insertion loss. We'll be using a National Instruments Compact DAC 9234 card for our data acquisition system, a small 2-channel speaker box for a source, and a PCB model 378 BO2 half-inch free field condenser microphone as our receiver. What we'll do is we'll take a gasket material and we'll put that on our speaker to avoid acoustic leaks, and then we'll put different panel materials in front of the speakers and measure the insertion loss. So we have 5 different panel materials. We have a 1/16 inch ABS plastic, a 1/8 inch ABS plastic, a 1/8 inch aluminum honeycomb, a 1/8 inch fiberglass material, and a 1/4 inch aluminum panel. So the first thing we're going to do for this demo is determine the maximum insertion loss that we can measure in this room. We'll do that by playing a sound through the speaker and then measuring the background noise in the room and subtracting the 2 levels. So first we'll play a sound. Now we're just going to record the background noise, and the program has automatically subtracted those and plotted them on the screen for you. So you can see the maximum insertion loss that we can measure in this room is about 60 decibels across the frequency range shown in the demo. We'll start with the thinnest material. This is the 1/16 inch ABS. It has a surface mass density of about 3.5 kilograms per meter squared. You can already hear the difference in the quality of the sound coming through that panel. And there is a plot of the insertion loss. So at 750 hertz we have almost no insertion loss with this panel, and at 3400 hertz we have almost 30 decibels of insertion loss. Next we'll move to the same material. This is also ABS, but it's twice as thick. This is 1/8 inch thick, and its surface mass density is 6 kilograms per meter squared. We see the green curve is the transmission loss of the 1/8 inch ABS. Now, if we look at the mass law calculations on the right-hand side of the screen, we would predict a 4.7 dB increase in the insertion loss between the last 2 materials. And we don't really see that until we get to high frequencies. The reason for that is more than likely leak area around the gasket with thin material. Next, we'll try an aluminum honeycomb material. This is also 1/8 inch thick, and it's almost the same surface mass density as the last ABS plastic that we used. But it's a double panel design with little air gaps in the honeycomb lattice. So the mass law would tell us that we should get the same insertion loss for the honeycomb material that we got for the 1/8 inch ABS. As you can see, at low frequencies, we get a slightly better insertion loss with the double panel material due to double panel transmission loss. Next, we'll go to a heavier material. This is an 1/8 inch fiberglass, and this is about 11 kilograms per square meter, so almost twice as heavy as the ABS plastic. So we should see about a 5 dB increase in insertion loss with this material. And you can see the difference in the green and the yellow curves here. And there is about a 5 to 6 dB increase from green to yellow, as the mass law would predict. Finally, we'll go to a very heavy material. This is now our 1/4 inch aluminum. We would expect this to block a lot of the sound. And if we look at the mass law prediction on the screen, going from the fiberglass to the aluminum, we would expect to see almost 9 dB higher insertion loss. And we see anywhere from a 5 to 10 dB increase at low frequencies, and at high frequencies we don't see a lot of increase, probably because of leaks around the edges of the gasket sealing system. So one important takeaway is you have to have very good sealing if you're trying to do high transmission loss work. Finally, I'm going to demonstrate a double panel system. So now we'll use the 1/8 inch honeycomb and the 1/8 inch ABS with a 1/8 inch air gap between the two of them. So now we have a panel system that weighs about 11.6 kilograms per meter squared surface mass density. It's about the same mass density as the 1/8 inch fiberglass. The single panel mass law would tell us this should have the same insertion loss. Let's see what happens. So you can see we get considerably better insertion loss with a double panel system, and that's because of the air gap. So in future demonstrations, we'll talk about double panel systems and the theory behind those. So transmission loss is a very important factor in the automotive industry, as well as the aerospace industry and building acoustics. And in conclusion, what we saw in this demo was that we can make a very good prediction of single panel transmission loss using just the surface mass density of the panels. But that's not the only thing we need to consider when looking at a transmission loss problem. Remember, the double panel example showed that we can make a very light, very high transmission loss panel using double panel construction. Additionally, any leak area around your panel mount will greatly affect your measured transmission loss. I hope this demonstration was informative, and I hope to see you next time.
For more information, visit PCB.com or give us a call at 1-800-828-8840.